Okay, so let's start. So last time we prepared, so we introduced Schwarzschild black holes, which I think most of you already know something about. But we are going to study them from a somewhat more precise and hopefully rigorous perspective. And after writing the solution and working out the geodesics, both time-like and null, we talked about some theorems which will help us to prove Birkhoff's theorem that the most general spherically symmetric metric is this one, and that in particular you don't have to assume that it is static. The fact that it is static is proved as part of the theorem. Now, last time I made one fatal mistake, which was to say I'm maybe working in d dimensions. Actually, everything that I did and also things that I'll do today can be done in d dimensions with very little extra work, but there is extra work. So certainly the solution I wrote is valid only in 4 dimensions, and I'm going to just stick to 4 dimensions for this entire thing. But eventually when I improve my notes, I might include some d-dimensional derivations. So for example, Birkhoff's theorem as stated works also in higher dimensions. However, there's a converse which doesn't work at all. So I'll discuss those things a little later. So last time we talked about distributions and foliations, and then we were set to prove Birkhoff's theorem, which I'll complete today. But I want to backtrack a bit because I forgot to do something which will help in the proof of Birkhoff's theorem also the way I want to do it, which is to introduce a coordinate system for the Schwarzschild solution called Eddington-Finkelstein coordinates. And we've already introduced them for Minkowski spacetime, and it's almost a joke there because it doesn't really do much. It's just a linear combination of some space and time coordinate. So, but it sets the state for what we want to do. So actually these coordinates I think are essentially invented for the Schwarzschild solution, but in Minkowski they were simply given by this. R and then plus r squared d omega squared. This in Minkowski it's trivial to replace that by any omega d, and the idea was simply that v is equal to t plus r, and therefore it is a ingoing so called the ingoing coordinate, and this really means that if v is constant, then t plus r is constant. Then as t increases to the future, r must decrease to keep the same thing constant, and that is what we mean really. So it's actually r which is the radial coordinate which is going in, but v is just called the ingoing coordinate. And then this can also be done with another coordinate called outgoing, which is called u, and then there's a minus sign over here. Okay, now so that's just to refresh our memory. Now, because the Schwarzschild solution is asymptotically far away, just tends to Minkowski spacetime, it must be the case that there is some formula, or it should be the case, there is some formulation of the Schwarzschild solution which asymptotically goes in those coordinates to this form of Minkowski spacetime, and that's what we'll look for. And the way we'll do it is to consider radial light rays. So last time we considered geodesics, both null and time-like and null, but then they were allowed to have angular momentum, and now we are just going to set that angular momentum to 0, and just going to say that the ray of interest to us is radial, And if it's radial, then of course in the metric d theta and d phi are 0, and so in the usual coordinates, where we already showed that the metric is this, so I need not write the rest of it. So now if I put this to 0, that will give me the null case, and if I solve this, I'll find that dt is equal to dr upon 1 minus 2gm by r, but there's a plus or minus because I'm taking a square root of the condition which sets this to 0. Okay, so in this case, plus is outgoing and the minus solution is ingoing. By the same logic, in fact, if you see, when r is very large, then this factor is basically 1, and then dt equals dr is what we mean by outgoing, and with minus it's ingoing. Okay. Now we've seen that Schwarzschild coordinates break down at so the TR coordinates. I'm always ignoring theta and phi because all the stuff we are discussing only is relevant for T and R, and these coordinates break down at what did I do? R equals 2gm because the metric simply diverges. Now it's well known that this is not a genuine singularity for a very simple reason, which is that we can calculate the curvature tensor of this metric and we can square it to get a scalar, and we find that then we evaluate it at r equals 2gm and we find that it's finite. So this is an exercise, maybe you've done it in a more elementary course. It's one of the standard things you do with this solution. Simply take this metric, which is of a very simple form, there's just one function involved, calculate all the Christoffel symbols, calculate all the curvature components, and then sum them up in this way to get a scalar. The advantage of a scalar is that it will be the same in all coordinate systems. So you don't have to do the work of examining every component of R mu nu lambda rho. And then you find that this is finite, which certainly indicates, and then you can actually, so it certainly indicates that, I don't think it precisely proves, but it certainly indicates that at R equals 2gm, there's nothing bad happening with the curvature. You would expect otherwise to see a curvature singularity. So if it's not a problem with the curvature, then it should be a problem with the coordinates. And it's a similar sort of problem that we know from let's say plane polar coordinates, where at the origin things appear to break down, or the metric appears to break down, it degenerates. Or even if you look at the surface of a two-sphere, then at North Pole and South Pole in these theta phi coordinates, where theta is 0 or pi, the metric again breaks down. And you can always change your coordinates so that this doesn't happen. Okay, so let's try to motivate how we would want to change our coordinates. Well, the motivation is contained in this equation, because you see, if we can find a new coordinate such that r star, such that the whole right hand side is d of r star, then dt is plus or minus dr star, and we are back in business, and there's no singularity. We don't expect a singularity. Yes, question.
For there not to be any problem at that coordinate, shouldn't each term of the R tensor to be?
Yeah. So in principle, one has to check that the whole each term is non-singular. But I think no. I think maybe not, because you see maybe it is. Yeah, maybe it is. Maybe one has to. Yeah, that's why I said that this certainly indicates that it's not a singularity. The best way to prove it, though, that there is no that it's a coordinate singularity, is to find the coordinates in which there is no singularity. And what I was just saying is that if I can integrate dr over that factor to be a new d of a new coordinate, it looks likely that I'll just get rid of the singularity right there. And so what I do is define a new coordinate r star by dr star equals dr upon 1 minus 2gm upon r. I just picked one sign. Well, the point is that actually this is the correct sign, because we always imagine that we are doing these manipulations when r is very large. Why? Because when r is infinite, then we are in Minkowski spacetime and we are completely comfortable with all manipulations we might do. So we always try to connect to that. So as you can see, when r goes to infinity, then dr and dr star are the same. And then r star is a coordinate which starts to deform with respect to r as I come in towards this Schwarzschild solution. Okay. And this, of course, is an ordinary differential relation, and so it can be integrated to give me that r star is equal to r plus 2gm log mod of 1 minus 2gm by r. Sorry. I wrote that wrong. R by 2gm. So actually it is mod of r by 2gm minus 1. And it's important that there is a mod sign here. So therefore this is actually well defined, except exactly at r equals 2gm this diverges. So this change between r star and r is not well defined exactly at that point. But it's singular at that point, but it's well defined for r greater than 2gm as well as r less than 2gm. Okay. So what is the key feature of this? So this has a name. It's a famous type of coordinate called the tortoise coordinate. And tortoise is, as we know, is an animal that moves very slowly. And the idea, now we can see that why it's a tortoise coordinate, because let's say r covers this much range from some point, could be 4gm or any finite point up to 2gm. During this time, what does r star do? It goes from this value all the way to minus infinity. So that is why it's called a tortoise coordinate. It takes a much longer span to reach there. Anyway, so now the interesting thing is that we are going to, so the interesting thing is that we are now going to, we have defined r star, but we are not going to make it a new coordinate. It looks like we are, but we are going to do something more clever. We are going to actually define v to be t plus r star, and now we will take v and r as the coordinates. This is the key idea of Eddington and Eddington-Finkelstein coordinates. So there are two steps. First we first we define r star as a function of r through this, which we integrate to get this integral. And once we've done that, we define a new coordinate v to be t plus r star. So in this process, we actually have got rid of t. Okay, but we retain r. So instead of the pair t and r, we use v and r. This is the key idea. Okay. So two things we are not doing, which you might have thought. One is that we might have defined u to be t minus r star, and then used u and v as coordinates. We could do it, but we are not doing it. Another is that we could have used r star and t as coordinates, which also we are not doing. And you are welcome to work out the metric in all these other options and you'll get something. But the most illuminating metric is actually the one which we get by treating v and r as independent coordinates. So r star is just an auxiliary construction, and the metric we find is minus 1 minus 2gm upon r tv squared plus twice dv dr plus, as usual, the angular part, which we haven't. Again, note that if we had actually used r star, we would be in some trouble, because here we have r squared d omega squared. We would have to treat r as a function of r star, which would be very complicated. So we actually gained a lot by just keeping r the same radial coordinate that we had before. What we've changed is from the time to v. Now the nice thing is v itself, for r greater than 2gm, and because of this sign, is still a time. It's a time-like coordinate, but it's not the same one as t. Okay, so the good thing here is that r greater than 2gm, it's well defined, this metric, and v is time-like, while r is null. This is exactly what I already showed you in the case of Minkowski. Because Minkowski is nothing but the infinite r behavior of this metric, and in that limit, v is time-like and r is null. Now it's very weird, and it takes really a lot of getting used to, that we have a radial direction, but it's null. Okay? Just a fact of these coordinates. It's some kind of, you might say, artifact of these coordinates. But because it's null, because there's no dr squared term in the metric. Yeah. Now let's look at r equals 2gm. Again, the metric is well defined. This term vanishes, and dv dr is a good metric. The metric dv dr is just the metric of 1 plus 1d space-time, where v and r can be renamed as v and u, and the other two null directions, which are linearly independent of each other. It's a perfectly good metric, but now v is null and r is null. Okay, and finally, when r is less than 2gm, again the metric is well defined, but v is space-like, and r just remains null. R is just always null, is not affected. Okay. Now notice, it's an easy exercise to convince yourself that if I have one time-like and one null coordinate, my signature is minus 1 plus 1. Time-like is minus 1, and there's a combination which is signature plus 1. So actually the metric still has negative determinant, and it has signature minus 1, 1. Apart from ignoring the angular part. If both are null and they are linearly independent, then again the signature is minus 1, 1. And if one is space-like and one is null, then again the signature is minus 1, 1. But v is no longer a time, v is a spatial direction. Okay, r is always null, and some combination of v and r will be time-like. Good. Okay. So we can do the following. So now you may ask, well, in the original Schwarzschild solution, we haven't gained much. We could have used that solution at r greater than 2gm and r less than 2gm. We only couldn't use it at r equals 2gm. But now we have a solution that we can use for all r. And there's a significant difference in these two statements, because in the Schwarzschild coordinates, we cannot interpolate from the outside to the inside of r equals 2gm continuously. We cannot follow a ray and say we are going to find out what it does as it approaches this r equals 2gm surface and what it does after that. We simply can't do it, because at some point our knowledge breaks down, and here we can. So in a way, the correct way to think of this is, imagine this is r equals 2gm. Then we can say that the Schwarzschild coordinates define a metric only outside. Then we say that, well, the Eddington-Finkelstein coordinates define the same metric but outside using some new coordinates. Now we extend this metric manually to inside. Okay, so in a way we have extended our space-time using these coordinates. Good. Okay. Now let's understand R equals, what is the nature of R equals 2gm? Well, we can understand this by finding the normal vector. So in fact we can ask what is the nature of R minus 2gm equals constant. Okay, and we've seen quite some time back that if we have a first of all it's a hypersurface because it's one condition on 4 coordinates. Okay, and we've seen that the gradient of this defines the normal vector, and and then we can study that normal vector. So the gradient is given by let's say del mu of R minus 2gm, and then if I want to find the vector field corresponding to this, I have to raise this index and I call this v mu, and I'm guaranteed that this will be a normal vector to the hypersurface. We've discussed all this many times. It's how we study hypersurfaces. But in this case, you see that nu has to be R, otherwise there is no answer because everything else vanishes. If nu is R, then this is R. And if this is R, then this has to be V. Because the only term in the metric which has one index R is GVR. And G upper VR is the same as G lower VR in this metric, and it's just 1. So therefore, in the coordinates VR theta phi, this is the vector 1, 0, 0, 0. Where this is V, this is R, this is theta, and this is phi. And this is a null vector. Well, actually I said that too fast, sorry. So now V squared is V mu, it's not a null vector everywhere. So V squared, V dot V is this. And this vector, if we find this inner product using the Eddington-Finkelstein coordinates, well, we are in those coordinates. If we just use that metric, the inner product is minus 1 by minus 2gm by R. And for R, when we started with R greater than 2gm, so this is less than 0. So for R greater than 2gm, so it's time-like. So we have a family of time-like surfaces, surfaces with a time-like normal, okay, which at every R equals 2gm. Okay, the surface which contains V, theta and phi. Okay, but at R equals 2gm, V dot V goes to 0 because this factor goes to 0, and so what we have is really a null hypersurface. Now I've just formalized what you already knew. Is the same thing as saying that the coordinate V became small v became null, but we simply said that, well, this is the normal vector to the null hypersurface, and as we know for null hypersurfaces there is this weird fact that the normal vector is also in the surface. It doesn't point away from the surface, it actually points along the surface. Good. Okay, and because of this, actually this statement, it's very innocent, is the state R equals 2gm is a null hypersurface, is a very, very powerful statement. It is in some sense responsible for all the weirdness of the Schwarzschild solution. So this is really the most important thing about it. Okay. Now we are going to examine this solution in detail by writing down null rays and examining how the null rays behave when we are outside, on and inside this null hypersurface. It's a fairly straightforward thing. But let me now go back to Birkhoff's theorem, because we have enough information to actually prove the theorem, and the theorem is very important because it says that just assuming spherical symmetry, we are led to this, this solution, and we haven't shown that. The unique spherically symmetric solution to the vacuum Einstein equations without cosmological constant is the Schwarzschild solution. So that is Birkhoff theorem, and now I'll give you a proof. Are there any questions about what we did above? Okay. So last time we defined a distribution on a smooth manifold and then talked about integral manifolds of that distribution, and and gave definitions for when this distribution is completely integrable. So the way to I didn't give you any examples, so it might have remained very abstract. So let's give you some examples. So examples of distributions. Basically, distributions lead to foliations. This is the key idea. This is which we defined last time. So to define a distribution, we had to take a subspace of the tangent space at every point smoothly. So it's a smooth assignment of a linear subspace of the tangent space at each point. So let's take a trivial case. Let's just take R2, two-dimensional Euclidean space. The tangent space is the space itself. A subspace at every point could, for example, be the horizontal line. In fact, it's the only sensible subspace because this is two-dimensional. But okay, let's actually improve the problem by looking at three-dimensional. Look at R3. Now I could have a one-dimensional distribution, and an example of that is this horizontal line in 3D. Okay, and it defines a foliation. So my claim was that, okay, first let me say what this line is. So this is an integral manifold of this distribution at each point, and I have to follow all the points in R3. So all the points going up and down as well as all the points going in and out will span all of R3, and there will be a line for everyone. Okay, so I'm going to fill R3 with lines. I won't be able to draw it very well. These lines will be going up and down, and they'll also be going back to front. And this will be a foliation in a generalized sense of R3 by lines. It's not a foliation by hypersurfaces because lines are 1D. So actually the parameter which tells you where to be in the foliation is the plane orthogonal to that line, and that's two-dimensional. Okay. So a foliation of dimension k on a d-dimensional manifold is a collection of disjoint connected immersed k-dimensional submanifolds. So in this example, k is 1. Okay, such that in a neighborhood of every point there is a smooth chart such that the neighborhood looks like a product of Rk, which is this, cross R d minus k, which is R2 in this case, which is the plane orthogonal to that line. Okay. So we have a foliation. A slightly more non-trivial example might be a surface of a sphere, so a two-sphere. Now I could take my foliation to be by latitudes. Okay, and we see that it's a good foliation except of the surface, except that it breaks down at north and south poles. But in any case, we may be content with considering the foliation in a finite region. Okay, good. Now, the usefulness of this is that in the case, okay, so then the key theorem that we needed for Birkhoff was the existence of spherical symmetry, right? Is the only data we have given. And spherical symmetry implies three vector fields v1, v2, v3 with the usual commutator brackets. And Frobenius theorem says that if the Lie brackets close, then this distribution, so if the Lie brackets close with these being in the distribution, then the distribution, that means these are in the tangent space of interest, then the distribution is involutive and we get a foliation. So this assures us a foliation given a distribution. So there are three steps: defining distribution, defining foliation, and then arguing that with a distribution we always have a foliation. And this time the foliation is going to be by two surfaces. And the purpose of this exercise was to write to get the metric in the form ds. So this is a general spherically symmetric metric in the form ds equals ds hat squared plus some unknown function h. Okay, so now I'm going to label. Now I have to introduce coordinates, right? Up till now we didn't have coordinates. So I'm going to do it like this. I'm going to say that, well, let's see which order I do it in. Yeah. So by two surfaces. So first I'll choose the coordinates theta and phi as the coordinates on those two surfaces. Okay? Because the two surfaces are actually spheres with these as the symmetries. And so it's natural to choose the usual coordinates theta and phi on a sphere. That leaves two more, and I'm going to give them the names u and r instead of t and r. And I'm going to claim that this is the general form of the metric. So what you can see is that so this requires a good choice of u and r such that they are both orthogonal to the coordinates theta and phi. Okay, that's why there are no mixed terms of the form du d theta or du d phi or dr d theta dr d phi. Those are gone. Okay, that requires a little bit of a discussion to make it precise, but I'm going to assume that this is possible. And now with this, we'll keep this function arbitrary and we'll try to get this into a convenient form so that we can implement Einstein equations. Remember, we've implemented spherical symmetry just in getting to this, but Birkhoff's theorem says the only solution of r mu nu equals 0 with this symmetry is the one we are looking for. So we obviously have to implement that. Okay. Now the next step is a rather important one. This in general will be of the form f u n r du squared plus, let's say, g u n r du dr. I'm putting a 2 here, plus let's say k of u n r dr squared. Now by one coordinate transformation, we can do one of the following things. We can either remove this term, making the metric diagonal, or we can keep the first two terms, or we can keep the last two terms. We can remove any one term out of these three. And the more old-fashioned treatments of Birkhoff's theorem remove this middle term. Okay. But you can see what's going to happen if you do that. You're going to land on a metric of the form this times this plus this times this. then you will really be, then you only got to fix these functions f and k. The problem, and of course h. The problem then is that this is going to be the t coordinate when you finally conclude, but then you'll get the Schwarzschild metric in Schwarzschild coordinates, which are only valid outside. And then you have to worry whether this is negative and this is positive, or this is negative and this is positive, because you want a Lorentzian signature metric, so you have to examine cases. There could also be cases where one or other one is null. So it's much simpler actually to just eliminate this by choice of coordinates. Because now, once we solve the Einstein equations for f, g and h, we can anticipate, and now I'm going to show you, that we land on the Eddington-Finkelstein form. And moreover, we'll find that this will be both plus or minus 2. In Eddington-Finkelstein, this should be plus 2 dVdr or minus 2 dUdr. We'll get both signs. So therefore, we'll get either ingoing or outgoing as we like, because both are possibilities. Okay, good. And we'll also get that the sign of this is negative. This is always negative for Eddington-Finkelstein. So all those are going to be outputs of our calculation. So now to calculate the functions f, g and h. So f is this, g is the cross term and h is the coefficient of the spherical term. Using Einstein equations, r min equals 0. So we have to write these equations. Let me also mention that in some books and some proofs, people directly assume that h squared is r squared. They say spherical symmetry means r squared d omega squared. But actually that is something that you can prove using Einstein equations, so I don't want to assume it. So let me mention here, I'll be following a very nice BSc thesis from Netherlands. I don't think it's on the archive, but you can Google this. It's a BSc maths thesis in maths. This is the author of the thesis, and it's called something like rigorous proof of Birkhoff's theorem. He restricts, unfortunately, to 4 dimensions, but actually his proof, I believe, can be recycled almost trivially to higher dimensions, except that the numbers will turn out a little bit different. Okay. Let me also then show you why the system is equally simple for 4D and higher D. So the question is, how many R mu nus do we need to compute? And in principle, since it's a symmetric 4x4 matrix, there are 10 components, which is quite a lot to write. Okay, but the metric does not have these mixed terms, and none of the coefficient functions also depend on theta and phi. Okay, so in practice, R will only have this R mu nu will only have components in the UU, UR, RR directions, and then in the angular directions. Moreover, there is a simplification which is, let me write R UU, R UR, R RR. Now then there is in principle R theta theta, theta phi and phi phi, but all of them can be encapsulated by saying that there is an RAB, where AB, the coordinates XA are theta and phi. And this, by spherical symmetry again, has to be proportional to the metric of a two-sphere. You can take this to be the metric of a unit two-sphere. So there's only one function here. So the total number of functions is 1, 2, 3 and 4. And you can see now from what's on the board, it absolutely doesn't matter what's the dimension of that sphere. Okay, because if you are working in d dimensions, then the foliations are by d minus 2 spheres. The unit d minus 2 sphere will have a metric gamma AB, and RAB will be the R in components along XA, which are theta 1 dot 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 up to theta d minus 2, and there will be still only one function. But it won't be exactly the same function that I have. Typically those functions have a d dependence. And I haven't worked that out, but you're free to do that. It's a very nice exercise. In fact, I'll probably give it as an exercise. Good. So now we need to start writing out, and this part is tedious. Van Oosterhout, who wrote that thesis, remarks that he used Python to calculate. He also writes before doing these, you have to do the Christoffel symbols, then only you write these. But he remarks that he used Python, and there are probably many other ways to do it. Let's start with R. So this is the simplest of all of them. It is, I hope my notation is obvious. Comma means derivative. So this is the simple one. Just two terms. RUR is a bit more complicated. It's H by 2G, 2F comma R, H comma R upon H minus half G comma R upon G plus G U G R. It's just really a painful exercise in partial differential equations. That's RUR. Then there's RRR. Sorry, RRR we already wrote. RUU. This is the longest one. This is F by G squared. By the way, one reason to write these coefficients, we today are going to set all this to 0, but you might want these things if you also are looking for not vacuum solutions, but solutions where R mu nu is some energy momentum tensor, T mu nu. In that case, you need these factors also. We are just looking for vacuum solutions today, so they are not relevant. So this I managed to factorize some of the terms which in most treatments have not been factorized, so at least I can write some of the terms quite quickly. We'll see that it's much more tedious to write the equations. Luckily, if we start solving them intelligently, we'll be able to do it very fast. There. That is R UU. And finally, there's RAB. Let me bring in RAB when I need it. No, I need it actually very fast. RAB has an interesting feature. It has a constant term 1 plus 1 by G squared F times HRR. I don't think the video will show the screen above some point, but I guess people who watch the video can always scroll back and forth. Plus H F R, and then how many brackets to close? One here, and remember everything is proportional to gamma AB. In our simple case, this just translates to saying r theta theta is everything in the round bracket, and r phi phi is also everything in the round bracket times sine squared theta. It's very trivial. But in principle, you can use any coordinate system on your sphere, and it really is not relevant. So this shows that. So there are 4 equations.
So
and yeah.
I think one bracket is not closed.
One bracket is not
On the second line,
closed.
one.
Yes, you are right. Thank you. My mistake. It should have been this box bracket should have been closed here, and this should be closed here. F by g squared multiplies the first line, and 1 by g multiplies the second line. Okay, thank you. Very important. Okay. RAB
F is multiplied to lot of terms.
1 by g squared is multiplied to all terms. So I think we should put a box here. And 1 by g squared is multiplied to everything except the 1. So there's a double bracket here. Yes. Good.
F is multiplied to what?
F, which F? This one? Oh. F, HRR. Oh, sorry, I forgot to close that bracket also. Thank you. Yeah. Yeah. No. Yes, this one. Yes. Sorry. Sizing was also an issue. So this bracket closes here, this bracket closes here, and square bracket closes with square bracket. Everything closes. Good. Okay. So we start with the first and simplest equation, RR equals 0. And from that, we find that G R upon G is equal to HRR upon HR. Okay. This is one possibility, but there's another possibility, which is that HR, so this or HR equals 0. You see that if H comma R equals 0, then both terms vanish. Yeah, because then H comma RR is also 0. But if I assume HR is non-zero, then I can divide through by it, and then I get this first solution. So they are like 2 branches. And now to check which one of these I should pursue, you look at RAB. And this feature that the first term is 1 independent of everybody is very important, because all the other terms vanish if HR is equal to 0. This has HR, this has HR, and HR. Every single term has H comma R in it. So this contradicts RAB equals 0. So it has to be ruled out. That means this has to be ruled in. Okay. Now this one basically says G is proportional to H comma R. So this one says G of U and R is a proportionality constant H comma R of U and R, but constant with respect to R, because this is an ordinary differential equation in R. So alpha is still allowed to be a function of U. Is it clear? Stop me if there's any non-clear step. I just integrated that equation in a box to get this. Now G was the second term in the equation in the metric. So my metric at this stage is ds squared equals f, which I have not made any progress with, du squared. But G I have made progress, so it is 2 alpha of U, H comma R of U R, du dr, and then there is plus H U R squared d omega squared. Good. So we got this far. Now the next step is to notice the following. Supposing I take an infinitesimal variation of H, just dH, in the same sense as du, dr, etc. I just vary H, which is a function of two variables u and r. Then this dH is the same as H comma r dr plus H comma u du, just chain rule. And I'll use this to replace this by this minus that. Where? In this. Because here is H comma R dr. So I'll get rid of that by using this second equation. So my metric now becomes, nothing's changed in the first term yet, but it will soon, plus 2 alpha of u du dH minus H u du. Is this clear? This step? Here I should have had H comma R dr, and I use this upper equation to do this. Okay. And you can probably see where I am going with this. So now I have a new term in du squared, so I have to collect it. So it's f of u comma r minus 2 alpha of u H comma u whole thing du squared plus 2 alpha of u du dh plus h squared d omega squared. And now what you can see is that I can drop I can choose h to be one of my coordinates. Okay, because the metric now is expressed in terms of d omega, du and dh only. Now what we'll follow this strategy is to redefine things and then relabel them back to what they were. And I hope that's clear by context. So now this whole thing I can just call a new function f hat. Since I didn't know f, I also don't know f hat. So I haven't lost or gained anything as far as this redefinition is concerned. This one is now alpha of u du dh, and the last one is h squared d omega squared. And now I am tempted to rename h as a new r. So I'll just write this as r hat. It's very temporary, these hats. I'll drop the hats as soon as I want to. So this, things are improving. First of all, the last term came into the form we want, r squared d omega squared, so we are happy. Now there's a mixed term du dr which will stay, du dr hat, but we can simply define a new coordinate u hat to be alpha of u, such that du hat is alpha of u du. Remember, whenever we do all these things, they work only when things are function of one variable. If they are functions of multivariable, then we can't simply do these things. For example, if this depended on u and r, I can't just integrate this equation in u. But fortunately, alpha was an integration constant in r and therefore depended only on u. Therefore, this equation will have an integral, and whatever it is, I just call it u hat. I'm not trying to, how to say, okay, wait, let's insert that fact here. So I'm not trying to integrate it because anyway I don't know what is alpha, but in principle I can integrate it. So now the metric becomes f hat of u and r Now du I'll replace by du hat divided by alpha of u. So it will be alpha of u squared du hat squared. Now here we have to understand that u is now a function of u hat through that. But I don't know f hat and I don't know alpha, so I'll just call this f double hat of u hat. This is how things are done neatly. Right? I don't know them, so I don't really care. I don't have to integrate anything. All I'm sure is that, okay, and r hat. I have to also eliminate r in favor of r hat by inverting that h function. Okay, good. Then over here I've got my desired simplification. It's just du dr hat, both hats, and here I've got my desired answer. So everything is looking great, and I'm down to one function. Okay. Now I take the step of relabeling back. So I write it as f of u and r. I just relabel back to the drop all the hats and double hats. Now something very silly and obvious. On one hand, you should say, well, I shouldn't do this because my Ricci tensor components I wrote down so painfully were given in terms of f, g and h. So every time I redefine something, I should have changed those components. But instead, it's so trivial, and it made me laugh when I realized it. Now that the metric is of this form, I'll calculate the Ricci tensors for this form. And they'll have the same form that they had before, with g being set to 1 and h being set to r. No other changes. So I can recycle my original Ricci tensors with this substitution. Okay. So now, unfortunately, we have lost r, u, r, which was a long expression. Let's try to find it. So this just says that g is 1 and h is r. So these are the two things you need to remember. And now we have to determine f. So let's keep scrolling till we find our Ricci tensors again. And here they come. This we already solved, so we don't need to look at it again. Okay. Now the UR equation simplifies because GR vanishes. So this goes, this goes, this goes, and we get F comma R, H, and H comma R is 1 because H is R. So F comma R and F comma RR. And so that equation, I wish I had space for it. Yeah, I can do it here. So RR equals 0 is twice upon 2 upon R F comma R plus F comma RR equals 0. Those are the only terms which survive from that. Then RUU equals 0 gives me something similar but a little different. So again, all the G comma R's have to go. That goes. That goes.
G comma U will also go.
G comma U will also go because G is just 1. This also goes. And 1 by G is 1, 1 by G squared is also 1.
HU also goes to 0.
HU also goes to 0, thank you. And HR is 1, this also goes to 0. So you see how much things simplify. Listen in this, if you see some horrible coupled partial differential equations, find the simplest one to solve and you never know what might happen. So good. So in the end we get F by 2 upon R I just wrote it this way because this looks like the previous equation, plus f comma u upon r equals 0. And now see, from these two equations, this part vanishes if this part vanishes. So we'll save this for later, but comparing these two or subtracting them with a suitable factor, I find that f comma u must vanish. And this is the key step because it's static, doesn't depend on u. U is the time coordinate, and now we have proved the most important part of the theorem, which is that the metric is static. Okay, and having done that, RAB equals 0 gives me 1. RAB, remember, is very nice because of that 1 in front. It's 1 plus f plus r f comma r equals 0. And this one is the, sorry, f comma r f comma r, yes. And this one immediately says that f is equal to 1 minus, what have I done? F is equal to 1 minus a by r. Right. This is correct. Because if I take f comma r for this, I'll get a by r squared. Multiply by r, I'll get a by r. Then I add that to f and I get one. No, I'm just worried whether I've got my ones right. It's a bit nightmare. Let's check. So I claim the solution is f equals 1 minus a by r. Actually minus 1 minus a by, I think I've just written it wrong. This is right. This is correct. It should be plus a by r, because let's just check, f comma r is equal to minus a by r squared. So r f comma r is equal to minus a by r. So f plus r f comma r is equal to minus 1. So this is minus 1 plus 1. Yeah, sorry, I had a typo in my notes. So f is minus 1 minus a by r. And actually that's the end, because I cannot fix a. A is an integration constant of this metric, and to fix it I have to go to the asymptotic region and use the old calculation of ADM mass of the solution, which I am not doing, which will determine that A is 2gm. Okay, it only fixes the solution, but obviously physics has to fix the constants. So finally, we get the metric. Now one thing happened which I actually again made a small mistake. I wrote that the metric is plus du by dr, but it was always plus or minus. And the reason is this. So I made a mistake earlier, and I'm really sorry for that. We defined h equals a new coordinate r hat, but I should have said h is plus or minus r hat. Both are possible. Okay, because both of them make the last term r hat squared d omega squared. Okay, so if I did plus, actually it's not a mistake. If I took plus and I got this form of the, so I finally got ds squared is minus 1 minus 2 gm by r du squared plus 2 du dr plus r squared d omega squared. So actually no mistake as such. That gives this, but you will recognize that the correct name for U would have been V. This is the ingoing coordinate Eddington-Finkelstein metric. Of course, calling it U or V makes no difference. But I could have also defined H equals minus R. That was an option. And in that case, this term would change sign. So I've got the Schwarzschild solution from spherical symmetry and foliation by solving Einstein equations. Yes?
I guess the sign, you choose the sign so that R hat is positive.
Actually, no, because R hat, the point is that H was not given any sign, right? H appeared in the metric only as H squared. So H intrinsically has no sign. It can be positive H, negative H gives me the same metric. Therefore, when I give it the name R or minus R, that doesn't affect the angular term, this term. It only affects this term where the exact integral dH was present. So I could have chosen dH to be minus dr without changing anything else in the metric. Okay, remember that this one was never H. You're never going to get 1 plus 2g m by r. Of course, you have 1 minus a by r, and a as an integration constant could be anything. But my point is that there's no ambiguity, twofold ambiguity in this sign, because this was obtained by resolving the Einstein equations after writing the metric in the form of the new r hat. So at that point, this gave whatever it gave, and then of course this ADM gives me that this numerator is 2gm, and people do experiment with things like negative mass Schwarzschild black holes with the opposite sign, so 1 plus 2gm by r, but that metric has weird behavior and nobody has, I think, been able to find a good physical use for it. Other than that, you can always talk about it. Okay. So we've done a very important thing here. We've shown that the spherically symmetric solution to vacuum Einstein equation in an open set of space-time is locally equivalent to the Schwarzschild solution in that open set. Okay. Now, one important thing is that if I have a spherically symmetric star which is undergoing collapse, and I hope we'll be discussing collapse at some point, I'm not totally sure, then a collapse situation is not a static situation, right? Because something is collapsing in time. But the metric outside the star will still be given by a static metric. It's quite weird. Weird and true. Okay. Another thing which this is used for, you might have heard many times, is that there's no in gravitational radiation, this mode doesn't give any radiation. So there's a direct application to gravity. That's why gravitational radiation starts at quadrupole. Okay. Now let's look at the converse. So I emphasize that everything in my derivation so far can be extended to higher dimensions in the way that I made clear. There will always be only 4 functions in the Einstein equation, and spherical symmetry in higher dimensions will imply this metric. However, there's a converse theorem, and the converse theorem is actually true only in 4D. The unique, and this theorem is due to Israel, the unique static. So now we assume static and asymptotically flat. By the way, we didn't assume either one, huh? Though implicitly you might say we assumed asymptotically flat by solving Einstein equation with 0 cosmological constant, because we know that a cosmological constant is associated to non-flat behavior at infinity. So good, asymptotically flat. solution to r nu equals 0 is the spherically symmetric, so is the Schwarzschild metric. So in this version, spherical symmetry comes out for free. You assume static and asymptotically flat and you get spherical symmetry for free. But this is only in 4D, and from 5D onwards, this isn't true simply, and we know counter examples like black rings and all kinds of interesting solutions to vacuum Einstein equations which are not asymptotically, which are not spherically symmetric. There are also solutions which are spherically symmetric. Those are called the Schwarzschild-Tangerlini solutions. So I'm not going to discuss it more, but let me just mention for d greater than 4, the Schwarzschild-Tangerlini. Let me at least write the solution since it's very easy. Is spherically symmetric. And it looks like 1 minus RH upon R d minus 3. So in Schwarzschild coordinates, this plus inverse of this dr squared plus r squared d omega d minus 2 squared. So what's new is that this is a power of RH over R. Also, this RH, which does have the same dimensions as GM, isn't exactly 2 GM, it's rather some factor, numerical factor times GM, which is easy to calculate, having to do with the volume of some sphere. Because the 2 in 2 GM is actually 8 pi over 4 pi. And 8 pi comes naturally with G in the calculation of the mass, and 4 pi comes from the volume of the 2 sphere, unit 2 sphere. In other cases, you will have to replace that with volume of the unit d minus 2 sphere. The point though is that this is spherically symmetric, that's fine. And if I assume spherical symmetry, then I will get this. But if I assume static and asymptotically flat, I don't necessarily get spherically symmetric solution. There are other solutions. So the converse doesn't hold. Yeah. Okay. Good. Now let's little bit start pursuing the black hole idea for 5 minutes, then 10 minutes maybe. Then I'll end for today, and next time we'll prove a little bit difficult theorem. Not really that difficult. So now back to the black hole discussion, and we haven't really proved that this Schwarzschild thing is a black hole. And to prove it, we need to prove that the horizon has some special properties. So what we can say up to now is that the Schwarzschild solution in Eddington-Finkelstein coordinates is defined for all R greater than 0. Okay. And now we can recycle our discussion of null rays, where we assume that they are radial and null. So that's the behavior of light traveling radially. And previously we saw that in Schwarzschild coordinates, radial null rays satisfy dt is equal to plus or minus dr over this factor. And we classified them as outgoing for plus and ingoing for minus. Now what do the same rays look like in EF coordinates? so it's asymmetric now. So we have to set minus this factor. Now we are going to work with V, which is our preferred Eddington-Finkelstein, because most of the time we are concerned with ingoing rays. It's the ingoing rays that we want to show that they never come out. So this plus 2 dVdr is the metric, ignoring the angle dependence. And it's this quantity which we have to set to 0 to find null rays. So the two solutions are obviously, one of them is just dV equals 0, and the other is dV equals 2dr upon 1 minus 2gm by r, and this is the same as 2dr star. If you remember, we integrated this equation without the 2 to define r star. So this. Okay. So this one means that dt is equal to minus dr star. Okay. This one, on the other hand, is dt equals plus dr star. Now you may say, what is this t? We are working in Eddington-Finkelstein coordinates, but since we are outside the horizon, or since we are outside r equals 2gm, which will prove to be horizon, we want to take the point of view of an observer far away, so we can be at infinity, and at infinity the natural metric is not the Eddington-Finkelstein form, but the usual Minkowski form. That is what an observer would naturally use as time. Okay, null time is not something we normally use, or not even null, but this v coordinate is not something we normally use. So it's good to think at infinity of the original Schwarzschild time as being the time. And then of course we see that from the point of view of infinity, this is ingoing and this is outgoing. And of course what you're probably saying is, this is a bit waste of time, because we already knew that there are two solutions, two null rays, and one is ingoing and one is outgoing. The point is that all this is true outside r equals 2gm, but now we can, with our Eddington-Finkelstein coordinate, we can repeat the exercise inside r equals 2gm and see what happens. And something different happens. Okay. So now the problem is that if we are now consider r less than 2gm, and there's a problem. What is the natural time coordinate we should use when r is less than 2gm? Okay, we shouldn't bring in r star when r is less than 2gm, because r star, if you remember, had a singularity in its relation to r exactly at r equals 2gm. It was very good to do outside. But it's not a good thing to use inside. So we shouldn't use the fact that v is t plus r star. So we shouldn't use Schwarzschild time, and in any case Schwarzschild time is not something sensible inside, because if I was inside at a definite Schwarzschild time, then I don't know how to connect that time to outside, because the Schwarzschild metric doesn't let me do it. Okay. So we use a different approach to define a natural time, and you can argue whether it's a good one or not. This one I was inspired by the notes of Harvey Rial. So remember, r is a valid coordinate and v is a valid coordinate. So we'll simply write v is t star plus r. This defines t star. Okay, we can do this everywhere. We could also do it outside. It's different from saying t plus r star. There we had t, the Schwarzschild time, and r star was the tortoise coordinate. Now we have r is the usual radius, and t star is just defined by this. V is already given to us. And so now what we want to do is to ask whether things are ingoing or outgoing, where t star goes into the future. One thing you can convince yourself is that far away, actually it's obvious, far away you know that v is t plus r. So if we were outside, T star would be T sufficiently far away. Okay, but now we are inside and T star is just defined by this. And now we have to look at the two null rays. So the first one is dV equals 0, and precisely by this equation, this says that dt star is equal to minus dr. And so of course it's ingoing, even inside. Okay? Ingoing with respect to the T star time. That means as T star increases, we are going to the future and R is decreasing. So that's what ingoing means. Now let's look at the other solution. Okay, one comment here. dV equals 0 was one null ray for all possible values of R, greater than 2 gm, at 2 gm, less than 2 gm. It's a condition which doesn't even depend on R. So it's perfectly reasonable to think that an ingoing null ray should remain ingoing at all times, and in fact at all radii, and in fact this also confirms that it does that. Is the other null ray, which is a little more in question, because that other null ray was dV equals 2 dr upon 1 minus 2 gm by R. So now we insert V as T star plus R, and we find dt star is this quantity 2 dr upon 1 minus 2 gm by R minus dr. And this is equal to minus of 2 gm plus R over 2 gm minus R dr. Remember, now we are at R less than 2 gm. Okay? So this quantity is positive, but there's a minus sign. So as T star increases, dr is again decreasing. So this is again ingoing, and this is the key result that makes a black hole a black hole. There's a usual ingoing ray, and there's a ray which, if we were outside, would have been outgoing, but since we are inside, it's now ingoing. And I'll draw a picture called a Finkelstein diagram, which will show you how that works, and then we'll stop. So I'll just wait to make sure you appreciate this point. Both the null rays are now ingoing. And it's a very simple calculation. It only required us to define what ingoing and outgoing means, and actually a lot of people don't do that. It was nice that Real gave this definition. This also has some problems which you will see immediately when I draw the diagram. But yeah, this is the situation inside the 2GM. And the diagram is like this. So let's draw the T star axis. And since we are in a radial situation, we don't need to worry. This is really a 1 plus 1D diagram. We really don't need to worry about any angles. Now here we have a dotted line which is R equals 2GM. Now the fact that there's one set of ingoing rays which are dV equals 0, we remember was T star plus R. So they are always slanted at 45 degrees this way. So these are the lines along which V remains constant. Right? Because such a line is T star plus R equals constant for different constants. And what you can see now, we can put an arrow because T star is our time, so it's going to increase upwards. So these are all ingoing null rays, and as I said, these are not doing anything special because they don't seem to care about the geometry. They're just dv equals 0. So what this r is doing makes no difference to the angle or orientation of these lines. Now, let's look at the other ones, first outside and then inside. If we are outside, the other null ray should just be at this 45 degree. T star equals r if we are far away. Okay, in Minkowski it would have been just like that. And so we can be sure that far away it is like that because far away we are like Minkowski. But as we get closer to here, it's easy to see, let me move this over here. It's easy to see both physically and mathematically that these bend round and go like this. Huh? Yeah, so Rindler is one way to see it. Another way to see it is just think very classic in classical physics. This is a gravitating object, and this line like this is saying that T increases a lot but R increases very little. Okay, that means the object is sort of slowing down the light, if you like. Okay, of course this is null, it's always null. This is the null direction. It's not that it has become time-like, but the shape of space-time is such that that R is increasing very slowly for increase in T, showing that these rays are struggling to sort of get away. So that is very natural. And then the light cone is, of course, you can just take at any point and you can get a local light cone like this. However, the light cone becomes a bit strange if I am very close to this horizon, but outside it becomes like that. You can see that from this, by the gravitating effect of this thing, it has tilted that way. Okay. Now, precisely on this dotted line, the null ray hugs the dotted line. And that's the statement that if light, I mean it's very sort of hypothetical and idealized, but if I suddenly create a photon on the horizon of the black hole, it struggles to get away, and it never does. It just remains on that horizon, that null hypersurface, because the photon follows a null ray, and the hypersurface is null, and it stays on it. Okay. So exactly here at this r equals to gn, the light cone now looks like one vertical and one there. This one never changes, so this is my light cone. And it's this alignment, vertical alignment, which means that the light cone, so this is the standard ingoing direction, always ingoing. This outgoing one is somehow failing to outgo, it's now stuck vertically. So for all time, r never increases. So it doesn't go out, nor does it go in, it just doesn't do either. Okay, then what's the shape inside? Well, it turns into this. So the second null ray is this one, and you can see that it still intersects. Okay, so I should have drawn it better. It will intersect the first null ray in a very, very narrow light cone, like that. But the important thing is the light cone has tipped over so much that if to go up, R must always decrease, R never increases. So you should follow from this light cone to this light cone to this light cone. And we have reached the fundamental property of a black hole, that there is literally no causal direction pointing outwards. There are no outgoing rays. No outgoing light rays, null rays, radial null rays. Okay. So the light cone has tipped over. Now, of course, one thing is that because the light cone has tipped over, remember T is a vertical line, T star. But now you see it's outside the light cone. What does that mean? T star is a space-like coordinate. V itself is a space-like coordinate, so T star is a space-like coordinate. So what happens is that actually both T star and R are individually space-like. Both are, as you can see, both are at this point, for example, both are pointing outside the light cone, but there's a huge cross term between them, dt star dr. That makes the metric Lorentzian again. And it means that there is a time direction. There's always, it's not that there's no time direction, but it's this direction which goes in here, like that. That's time-like. It has to be in the light cone. So there is a linear combination. If I diagonalize the metric, I will certainly find one coordinate which is time-like. But it's because the cross term is very large. Otherwise, it's absurd that both t and r could be space-like. But they can be, I mean, individually. That means dt, if I move an amount dt without moving an amount dr, I undergo a space-like shift. If I do same in the other way, I undergo also a space-like shift. If I cleverly move both dt and dr so as to go that way, then I'm undergoing a time-like shift. It looks like, at least in our coordinates, that most things are space-like and there's very little chance to be time-like, but that's just a meaningless statement. You can always stretch that back in some coordinates. What is meaningful is that the causality direction has changed, so there's no outward direction. Yeah. Any questions? Okay, so because of this, we are entitled to call r equals 2 gm a horizon. In fact, r equals 2 gm is our first example of what is called a trapped surface. We will give a formal definition of a trapped surface when we discuss Penrose singularity theorem. Precisely because that theorem doesn't apply only to is not supposed to be for Schwarzschild. We already know now what Schwarzschild is doing. If we just wanted to know what this black hole is doing, we can solve these simple equations. We want to know, in principle, what are astrophysical black holes doing, which might not be anything like Schwarzschild solution. In fact, most of them are, or all of them are Kerr solution, which is something more advanced. Without going into the details of those solutions, Penrose managed to show that this closed trapped surface is a diagnostic for forming a black hole. And it's the horizon of the black hole. Well, one of them is the horizon, and then there are trapped surfaces inside all the way. So we'll do that. To conclude, let me just, I've gone on a bit too long. Let me just state in words, next time I'll write it. Just because we proved that there's no outgoing null radial null ray, doesn't mean we have proved that there's no outgoing ray of any kind. There might be a clever null ray which goes along the angles and somehow gets out, or there might be a time-like ray for all we know that somehow makes use of this geometry to get out. Intuitively, if a radial ray can't make it out, then nothing should make it out. And most discussions end there. Elementary discussions of black holes will say, well, with this simple calculation, we have concluded that nothing can get out of the black hole. But right now, we have only concluded that radially moving light cannot get out of the black hole. So the theorem says, in a Schwarzschild spacetime, there is no future pointing causal curve that goes from r less than or equal to 2 gm to r greater than 2 gm. So we'll spend some part of the next lecture, next Monday, to prove that, state and prove that. Questions?